So hello everyone, how are you all? I hope you all are fine and safe. Well again, welcome back to Quantum Mathematics. I'm Aman, just welcoming you all to a new amazing video. Well, we are just going to continue our series in which we were talking about the let me just put it aside here, six most fundamental integrals proof, right? And in which we did the first, that was sine of x, we did proof of that. The second, cosine of x. So we did these two integrals in the very first video of this series, right? And then we just moved on to the third one, that was integral e to the x dx, and the fourth one in the last video, that was x to a to the x dx. So we did these two integrals in the second video of this series, and now we are with the third and final, last but not the least video for this series, in which we are just going to prove that integral of secant squared x dx is tangent of x, and the integral of secant x tangent x equals secant x. So we are just gonna talk about these two integrals in this video, actually their proofs, and then we will be ending up with the series in which we have talked about all the basic integrals with fundamental integrals actually, and which we rarely just see the proof of them, but actually it's really important to understand why does they exist like that. So I think we should begin, and let's begin our journey with these two integrals. And again guys, if you just follow these all these three videos that I'm just going to upload here, and I will be end up with the three integrals, like three videos actually, in which we discussed about six integrals, like these six ones, right? So yeah, you will have a better knowledge about why integrals are like that and how we can look. You know what? Something crazy. Let me tell you that. So actually, so far we understood that if I'm assuming that integral small f of x dx comes out to be capital F of x, right? So if we take a derivative of capital F of x, so we would be having small f of x, right? So basically, you know what, if you are, maybe you can just use it sometimes, if you are getting struggle with the evaluation of this function, right, the integral of that function, so maybe you can go with, oh my god, actually it's not right actually, or maybe we can just consider it as, if you have solved an integral but you are not sure whether it is correct or not, and I'm talking about an indefinite integral, right? So if I got a result of capital F of x after integrating the small f of x, so if you want to check your result whether this result is right or wrong, so you can just go with this formula, like this expression. You just have to take the derivative of this function, the one you just got in the result, in the form of result after integrating this function, and if you take the derivative of this one, and if you got this function, right, so you can say that you just evaluated that integral correctly, and that's fine, that's exactly equals, and that's exactly valid, right? So that is why these two things are really important, and they are they are just depending on each other actually. So if you are finding any kind of trouble with or understanding whether your solution is right or wrong, so you can just go with that and you can just find that you did right or wrong, right? So it's a good thing, I think. But now let's just continue on the proof. So firstly we will prove that integral of secant square x dx is tangent of x. Fine. So basically here we are having small f of x is secant squared x, right? And capital F of x is tangent of x. So if we take the derivative of the capital F of x like this, or maybe we should write f of x exactly tangent of x here. So if we are going to talk about the derivative of tangent of x, and again, if I'm getting this equals, actually I should just consider writing here, if it equals to secant squared x, hence this integral is proved and this integral is valid. So let's just check that out, right? So basically, as we have studied so far, that yeah, let's take the derivative of tangent of x. You know what? Let me just write that down here. So f dash x is, if you are taking the derivative of a function, it is limit h tends to 0 of f of x plus h minus f of x over h. So this is the definition of the derivative actually, right? So let's just apply it here. So this is f dash x equals limit h tends to 0. So when you replace x with x plus h here, so that's gonna give us tangent of x plus h minus tangent of x, f of x as it is, over h. So far we are having this kind of result, right? And now we're just going to talk about this tangent of x plus h, right? Well, you know what? Let me just promote a video of mine here. Okay, so if we talk about tangent of x plus h, so that can be easily expanded if you know the formula, right? And the formula is, it is tangent of x plus tangent of h over 1 minus tangent of x times tangent of h. Or if you don't know about this, so you can just prove it by your own. You just have to go on the video of mine in which I just proved that sine of a plus b equals sine of a cosine of b plus cosine of a sine of b, and so for cosine of a plus b, which I proved as cosine of a cosine of b minus sine of a sine of b. And using these two equations, we can just easily evaluate this one, because tangent of x plus h is sine of x plus h over cosine of x plus h. So if you plug these two results over here, so you're gonna have this one result here, right? So yeah, we can just check that out. Well, you can just check that out by your own. It's not difficult. It's pretty easy, right? But if you're not sure about these two things, so you can just check that out, in which I just proved both of them using the most famous Euler's formula, this one. So that was really amazing, guys, and I just proved that using, like, it was really amazing. So please, I would recommend you to just watch that video. So now we're just going to plug this result over here, and let's see what we're having. Right? Yeah. Okay. So our f dash x equals limit h tends to 0, right? And that was tangent of x plus tangent of h over 1 minus tangent of x tangent of h, and minus tangent of x over h. Oh, let me just see whether you can just it is visible to you or not. Yeah, I'm pretty sure that you can see that. Okay, so now we're just going to take the LCM, or like, well, let me just do that here. So in the numerator, we are just going to multiply and divide. Oh, I'm sorry. Yeah, let's just multiply with 1 minus tangent of x and tangent times tangent of h, and divide with that also over there. So we are gonna have limit h tends to 0. This one is gonna cancels out, so we would be having tangent of x plus tangent of h minus tangent of x, this one, times this whole form, 1 minus tangent of x tangent of h, and over we are having h times 1 minus tangent of x tangent of h. Okay, so it's pretty fine, right? Okay, now it's good. And what next we're gonna do here? Well, maybe we can consider something over here. Wait a second, guys. I think I should just expand this out. Yeah, okay. F dash x equals, I'm just gonna multiply this one into this parenthesis, right? So it's limit h tends to 0 of tangent of x plus tangent of h and minus tangent of x with this one, and then it's negative tan, so it's gonna be a positive here, so it's plus tangent squared x tangent of h, and we were having h times 1 minus tangent of x tangent of h. Yeah, it's pretty sure here. Wait a second, guys. Actually, my AC is not working. I think I gotta be careful about that. Yeah, it's fine now. I'm sorry, guys. Okay, so now let's just erase this here. Okay, so now what we are gonna do here is again, look, this tangent of x with this negative tangent of x cancels out with each other successfully, guys. Yeah, it's pretty fine so far. So let's consider f dash x here again with limit that h tending to 0, and we are having tangent of h plus tangent squared x tangent of h over h times 1 minus tangent of x tangent of h. Now what we are going to do here, we are just going to plug a factor of tangent of h from the numerator, right? So we're going to have limit h tends to 0, so that if you plug out tangent of h, so that's going to give us 1 plus tangent squared x. That's pretty fine, and it's over 1 h times 1 minus tangent of x times tangent of h. Okay, it's pretty fine right now. And you know what? This is secant squared x. So yeah, well, since secant squared x is independent of h, so we can just plug that out in front of the limit, right? So basically we are having f dash x equals secant squared x, then limit h tends to 0 of tangent of h over h and 1 minus tangent of h x tangent of h. Okay, now next what? Wait a second. If I'm just going to plug tangent, h equals 0, so that's gonna just make this word explode. Okay, but I think I should just convert them in sine and cosine instead of just going with tangent, because I think that's gonna be quite helpful. I'm not sure, but let's just check that out. Wait a second. But because what's tangent limit h tends to 0 of tangent of h over h? What's that? Wait a second, I think it's 1. Yeah, I think it's 1. And if we plug here 0, well, let me just say it clearly. Basically, if we talk about these two things when I'm combining them to each other, so basically they are going to give us 1, right? Well, we need to use L'Hopital rule because directly it's not possible because it's 0 by 0 form. So eventually I'm not going to use that because I'm just proving that down. I'm just proving the derivative of this one is this, so I'm not going to use that. But yeah, it's an identity which says that tangent of h over h is, well, when limit h tends to 0, it's 1. Wait a second, let me just check that out, right? Oh, I'm sorry guys, actually, yeah, my phone just fall off. Yeah, it's fine. I'm really sorry guys. I'm really sorry about that. Yeah, I've just calculated that. I was not sure, that's why I just take a pause here, and my phone just fall off. I'm really sorry about that. Okay. So yeah, it's pretty sure that when limit h tends to 0, tangent of h over h is 1, right? Well, I just thought about that earlier, but I was not sure, that's why I couldn't use. And when we talk about here, so when you plug the 0 here, so tangent of 0 is 0, right? So basically this term is 0, and we would be left with 1 only. So basically we got rid of this with 1 only, right? And finally we just got this result. And hence we can say that the derivative of tangent of x is secant square x. Hence, by the integration and differentiation relation, we can say that the integral of secant square x is tangent of x. That is what it makes so cool, guys. And now let's talk about the sixth, the last but not the least integral in this video. That is the integral of secant x tangent of x, which we have to prove it to secant of x. So prove that integral of secant x tangent of x dx equals secant x, right? Okay, fine. So, well, again, let's talk about the small f of x here. So it's secant x tangent of x, and if we talk about the capital F of x, so it's secant x. So we just have to take the derivative of secant of x here. I'm sorry. That is d over dx of secant x. Fine. So again, we're just going to begin with our simple derivative test that says that if we talk about this one, so this is f dash x limit h tends to 0. Well, we're considering this as f of x here. So it's secant of x plus h minus secant of h over h. So we just have to just look after this limit here, right? Okay, fine. Let's just consider just writing it in terms of cosine, right? Because it looks quite weird and we're not perfect with that. We're not comfortable with that, right? But we are comfortable with cosine and sine things, even tan things actually. So it's limit h tends to 0. We can write this as cosine of x plus h minus 1 over cosine of x over h. Now again, just using the expansion of cosine of x plus h, I have discussed it in the last integrals proof. That was limit h tends to 0. This can be written as cosine of h times cosine of h minus sine of x times sine of h, and minus we are having 1 over cosine of x here over h. Fine, it's pretty fine here. And now we're just going to take the common denominator, and like to neutralize them, we just have to do something in the numerator of both of them, something like this. So we are gonna consider f dot x here with limit h tends to 0. How are we gonna do that? Well, it is cosine of x times cosine of x times cosine of h minus sine of x sine of h, right? So to neutralize this, we have to just write here cosine of x with a negative, and we just have to write this one here, cosine of x cosine of h minus sine of x sine of h. over h. Oh my god, that was quite complicated and messy. I think I'm not sure whether you were just looking all the stuffs clearly or not. Yeah, I think it's fine. It's pretty fine. Okay, now what we're gonna do here is maybe we can just wait a second. Let me just have a look at that. So we can write that as f dash x here is the limit h tends to 0. Well, I can just multiply this negative one in this parenthesis, so we're gonna have cosine of x minus cosine of x cosine of h plus sine of h over, we're having h times cosine of x times cosine of h x cosine of h minus sine of x sine of h. Actually, I just multiplied this with this denominator. Actually, that's what I did, and if you cannot see that clearly, it's not difficult to understand that I just multiplied this one over here. That's it. Okay, now let me just do something with that over this board. Fine. Okay, so next what we're gonna do here is, wait a second. Yeah, I can just break this with two different limits. I think I should just consider this one as the first one and this one as the second one, because from this one I can just take cosine of x as common, and yeah, let me just do that here right in front of you. So f dash x is limit h tends to 0. Well, I'm considering cosine of x minus cosine of h cosine of x over that big chunk of things, that is h cosine of x cosine of x cosine of h minus sine of x sine of h, and then we have a positive sign over there plus limit h tends to 0, and we are having sine of h over h times cosine of x times that big chunk of things again, cosine of h minus sine of x sine of h. Okay, so we have just separated two different kind of limits from this one. Now if we talk about the first one, so we can just do something there, that is we can just factor cosine of x out of the numerator actually. So we're gonna have limit h tends to 0 cosine of x 1 minus cosine of h over h cosine of h. Well, since this cosine of x cancels out with this one, so that's a pretty big good thing. Cosine of x cosine of h minus sine of x sine of h. And now, since this sine of x over cosine of x can be written as tangent of x, and since it's not depending on x, so that's just gonna plug out of the limit. So basically we're having tangent of x and then limit h tends to 0, right? We can just write this as sine of h over h and times this big chunk of things again, cosine of x cosine of h minus sine of x sine of h. Okay, now it's fine. Well, you know what? Let me just do this here. Two things to be known. Limit h tends to 0 of 1 minus cosine of h over h is 1, and wait a second, is it 1? Yeah, it's 1. Yeah, you just have to be careful about that. It's 1. Oh, I'm sorry, wait a second, is it 0? Yeah, is it 0? It's not 1 actually, I'm sorry. It's 0. And if we talk about here, so it's 1 and it's it's 0 guys, it's 0. So this is 0, right? And limit h tends to 0 of sine of h, actually h over h is 1. So these two things you just have to just keep in mind that we're going to use over here. And you know what, where? So the first one would be using here 1 minus cosine of h over h. Since h is tending to 0, so this whole part is going to be 0. And if we talk about this one part, so this is 1, right? Well, we just have to care about when h is 0. So this cosine of 0 is 1, so this is going to be 1, but this part is going to be 0 as well. So let me just see. Well, it's kind of reflection of that. Oh, let me just write that down on that board actually. Maybe you are having some sort of trouble with reflection actually. I'm sorry. Okay. So what I just said over there is that some properties are there. The first one is limit x tends to 0 of 1 minus cosine of x over x is always 0. And the second one is limit x tends to 0 of sine of x over x is always 1. So these two things we're just using them right now. And you know what? We are left with f dash x equals, so this part is 0, right? And we are left with tangent of x from here. And from here, this part is 1, this part is 1, this part is 0. So basically we are left with this 1 over cosine of x. 1 over cosine of x. That basically says that f dash x equals tangent of x times secant of x. So this is how we can just consider those things. And yeah, I just messed up slightly in the between of the video, but I'm really sorry about that. Still, I'm a learner, so you can just thought about that. So now, if the derivative of secant of x we began with comes out to be tangent times secant of x. So hence we can say that the integral of this function is gonna be secant of x, and hence proved, guys. So this is how you can just talk about all of these 6 basic integrals and their proofs. And yeah, it's pretty easy to evaluate or prove them. I know it's kind of difficult to just solve this kind of limits because we did a lot of messy things like in this video, like my phone just called off, and I'm extremely sorry about that, guys, but it's all right. I'm not having a proper stand for that, so I just have to place it over something, so that is why maybe it's an accident, but it's all right, guys. Again, if you got to learn something from this video, guys, just make sure to just like and subscribe. And if you got any kind of doubt here, and if you just noticed me something wrong, so please, it's your responsibility. I'm just giving you a responsibility to just catch me if I'm wrong somewhere, and you just have to tell me freely. Look, guys, I just want to improve myself, and how would I able to improve myself? If I would know what is wrong in me, and if I'm just going to correct all the things, so I'm improving myself. That is why I just want you to tell me where I'm wrong, whatever, like my teaching style or my phone's quality or my writing or anything else, anything I would really try to just cover that up as soon as possible. So yeah, thank you so much for watching this video, guys, and goodbye, take care. And again, I'm just going to bring some crazy things for you guys. I'm in progress with that, and those things are really crazy because we're just going to play around with Euler's life. Yeah, it's pretty fine. So goodbye, take care, and be careful. Well, I'm not going to attack you, but I'm just saying that death is unexpectable, or anything is unexpectable. So please get rid of that and be careful. Love your life, and I love you so much. Goodbye, guys.